Yeah, so we actually carried out a study here at Ames back in the days when XPRM was still alive and the agency wasn't revectored yet again, to explore the possibility of a very, hopefully, low cost and low impact um, mission to the surface of the moon, and specifically to address the volatile question from the point of view of resource utilization. Because we recognize that you can't just take a volatile processing plant, go to someplace on the moon, and be guaranteed to actually get the things that you want. You might send it there and then find you're in a dry hole. So, as with the Earth, you need to do prospecting. So looking for resources on the Earth requires you to answer the following questions. Where are the resources of interest? What form is it in? How much is there? If it's not that much, then it may not be worth recovering. And how do you extract it? Another thing. All these things are elements of the economic geology that tells you whether or not you can actually make use of a resource and beneficiate it. So in the case of lunar ISRU, if the resource cannot be mined and processed in a cost-effective way, and that means also from the point of view of energy and the point of view of actual operability on the surface of the moon, then it's of no use. And so if you find, for example, that going into a location of extreme cold, such as at the poles of the moon, it may be just too hard to actually exploit those resources, and you would resort to a different set of resources, those that are found at lower latitudes, for instance. And of course, we know now that all parts of the moon are not alike. The poles are certainly a lot different from the lower latitudes, just as all parts of the Earth are not alike. You don't necessarily find oil everywhere. There are specific geologic settings, of course, where it's likely to be, and even then, you find dry holes. So we really need to obtain, in order to do the cost-benefit analysis, you really need to obtain the best possible data to inform where you need to go to extract resources. And so this Polar Volatiles Prospector mission has two overarching goals: to confirm the evidence of volatiles and their distribution at the scales that Tony was talking about in the last talk. Namely, we have a point from Lcross giving us a certain abundance, but we also have a very much larger scale based on orbital data and there's a huge gap in scale in between. And that really defines whether you can beneficiate and use resources or not. So the second thing is, once you actually get there, determine if the volatiles are in a form at that point to be exploitable. It may be that they're too finely disseminated to actually be recoverable in some sort of meaningful way. So what is the actual form that those volatiles are in? So we want to do two things. We want to measure the subsurface volatiles, those that were excavated by Lcross, for instance, so disseminated ices, maybe blocks of ice, and other substances disseminated throughout the regolith, but also look at the surface-bound volatiles, these H2O and OH signatures on the surfaces of grains, clearly increasing with latitude. And this also may constitute a beneficiable resource, but we need to know what the concentrations are. So we're going to be looking at two possible polar landing sites: a short-duration daylight site, one that actually is in the floor of Cabeus, in which we would be able to explore this question of the subsurface and surface-bound volatiles, and another more persistently lit site, one of Ben Bussey's favorite places, the rim of Shackleton, where you get a very long period of sunlight. And there, you do not expect to find ices because the mean temperature in the subsurface is too high, and you would find the surface-bound volatiles only. So to start with the subsurface volatiles, the rationale is, of course, we've seen evidence from orbit and from Lcross that there's plenty of hydrogenous stuff at the poles of the moon. And the question is, what is the form? How is it distributed? Is it too deeply buried to make use of? Questions like that. So we need to confirm the presence or absence of these things, quantify their spatial distribution, the lateral and vertical scales of the distribution, quantify the form. Is it ice? Is it other chemical compounds? And is it readily available near the surface of the regolith, or do you have to go and mine it very deeply in order to get to it? We also need to understand what the geology is, the geologic setting in which we find these things, because if there really truly is lateral heterogeneity in the distribution of these things, clearly geology is controlling it, and the principal geologic process taking place on the moon today, of course, is impact and gardening. The surface-bound volatiles, again, this is a question. We see these things on the surface of grains. The question is whether they're volumetrically really important or not. So we need to go there, take a look at how they're distributed, find out if they change over the course of a day, and then also establish whether they're volumetrically important. Again, this is the main thing. If it's just monolayers on grains at the surface, then it may not be worthwhile trying to beneficiate it. And again, as in the case of the subsurface volatiles, characterize the influence of local geology on the distribution, and whether mineralogy and so forth has a controlling factor, as it seems to, based on remote sensing. So here's our little nominal payload, and I expect to hear some pushback on some of this, but we carry a neutron spectrometer, a near-infrared spectrometer, and a pneumatic excavator. This stands in place of a very massive drill. The idea here is you're using gas to excavate layers of regolith, layer by layer, in order to expose the subsurface down to potentially 20 centimeters depth and probably below, depending on the structure of the superficial layer. And so it's a fairly limited payload, and therefore trying to get at a lower cost solution to the problem. The concept of operations would be that the rover is teleoperated from Earth with ground control. We'd continuously be monitoring data coming from those instruments and from the navigation camera, and base all our decision making on that. However, if the rover happens to go into a calm blackout because of the topography of the landing site, which we would try to avoid but might not be able to avoid, then it would stop and it would back up into the last location that it had good comm and reestablished comm before going any further. It's kind of like a safe mode for an orbiting spacecraft. The total distance traveled, we reckoned, would be many, many tens of meters up to hundreds of meters, and actually to explore a large range of geologic settings. And by that I mean different crater ages, different crater sizes, and so forth, because the ejecta blankets may be the place where the ice is more, or ices and other things are more readily recovered. In terms of excavations and what we would do with the pneumatic excavator, we would baseline 10 excavations and try to get as many as possible along the way. And in terms of the actual mission timeline, this is a rather sporty mission. As you can see here, it may not be achievable, but this is what we're laying out just based on the constraints. The first day we would land, we would check out and deploy the rover and make sure that everything is working. And then for the following about 2 to 4 days, we would traverse as far as we possibly could to get to 3 kilometers, and stopping along the way to do these excavations. The spatial distribution of subsurface volatiles, as I said earlier, is controlled by impact processes and gardening. And so the idea here is that in order to get at this question of the lateral and vertical heterogeneity, you need to visit several different sizes and therefore depths of craters. We're really likely to see that the top half meter or so of the landing site is going to be very, very patchy at scales of perhaps as little as 10 meters, as Dana Hurley has been doing calculations, to perhaps as large as hundreds of meters. And for that reason, we need mobility. That's the reason why we can't land in one place and do this and answer these questions. In order to perform this mission, of course, you've got site selection criteria that enable the mission. You can't do without the subsurface volatiles. That's why you're going there. So you want some kind of indication that A, the temperatures in the subsurface are low enough to retain, for example, H2O ice for a significant time, and B, that there's some evidence from the orbital data. Where our best information from orbital data is that there's a hydrogen enhancement there indicating the presence of these volatiles. We need sufficient daylight illumination, so that means a location where you can get at least 4 Earth days of solar power for roving operations. I'm assuming that we don't take nuclear with us on this mission. Oh, and it also provides us a clement surface environment in which to operate, as opposed to permanently shadowed regions where you have to deal with 40 Kelvin and below. A key to this, of course, is the direct-to-Earth communications. We need that DTE all the time, or as much of the time as we can safely do so, with DSN stations clear of the horizon. We need traversable terrain. What that means is slopes less than 10 degrees for roving, and a limited density of rocks in terms of hazards. So the intersection of all those things is what we're looking for, and I'm really focusing on 2 locations again here, as I mentioned earlier. Here's the Lcross impact site. This is Cabeus. This is the topography of, thanks to Lola. And the Shackleton Rim down here is, of course, very close to the South Pole and gets a lot of sunshine, and it's above the local surroundings. This is the days of sunlight in May of 2017, our notional mission time frame. And you can see on the Cabellas floor at the site, not too far away from the Lcross impact site, you actually get as much as 6 days or so of sunlight during the month of May. And then, of course, down here at the Shackleton Rim, being closer to the pole and much higher, you get in excess of 2 weeks worth of continuous sun at that location. In terms of whether or not you're likely to find stable ice at these locations, this is Dave Page's depth to stable ice calculation based on the surface temperatures and modeling it of diviner data. And in particular, you can see here that Lcross landed in a place that's in permanent shadow. It's also very, very cold, and it means that you can have ice stable right at the surface, 0 centimeters below the surface. But as you move away from that location into other locations that receive a little bit of sunlight, like, for example, the 4 to 7 days that we were talking about for this mission, you're still within 10 to 20 centimeters or so of the surface, and that's accessible real estate, subsurface real estate. That makes it very appealing from that point of view. Down here on the Shackleton Rim, not so much. There's no ice stability within meters of the surface at these locations because the mean temperatures are too high. I'll just overlay some LEND data. This is from a recent league abstract. I ripped out the map for this. So this shows you the epithermal count rate in this, sorry, that's not the right color scale, but anyway, the lows here indicate increased hydrogen and suggest that, if I go back and forth, there is an enhancement in hydrogen in the locations where there is, where the depth to ice is actually fairly shallow, and not so much down here at the rim of Shackleton. There's basically no feature. Both Lunar Prospector and LEND say that. So this is, I'm painting a kind of a grim picture of Shackleton Rim, but you know, it's great for sun, not much good for much else. Now, in terms of slopes and stuff, this is just to illustrate. We also have slopes, obviously, from Lola, and we can also establish slopes based on imaging data. Beautiful L-rock images have been taken of this area, but specifically, I just want to point out that in this location, the Goldstone topo map gives you slopes that are less than 5 degrees throughout most of this, less than 10 degrees throughout much of the area we're considering here. So this would be a trafficable area, at least as indicated at the 40-meter scale. Shackleton Rim, not so much. Again, it's the rim of a crater, and navigability, trafficability at that location is problematic, to say the least. There's also the environmental, the temperatures that we have to deal with here at night. This is minimum temperatures from the diviner model. As you can see, it gets well below 100 Kelvin. This is very stressing. And of course, in the daytime, you get up to reasonable temperatures, and so you can operate in that time, during that time. But the bottom line is that nighttime survival doesn't seem to be feasible for a mission of this kind. So you have to accomplish everything basically in one go. Okay, so let's compare the two landing sites, Cabellas Floor versus Shackleton Rim. Subsurface volatiles, very, very likely based on a bunch of different data sets. Certainly it's cold enough. Unlikely at the Shackleton Rim because it's not cold enough. The depth to the frost line can be very, very shallow in the even occasionally sunlit locations inside Cabellas. Not at Shackleton for sure, because it's just the subsurface temperatures are just too high, and so that's true down to meters in depth. Neutron spectrometer signature, yep, it's good there. Not very much at Shackleton. Surface-bound volatiles, you're bound to find at both locations in all likelihood. I don't see any reason why you wouldn't see them there in both locations. Daylight duration 4 to 7 days versus more than 2 weeks in the case of Shackleton. So this favors that location, but that's really the only thing. Direct Earth comms is important because you really want that to establish that two-way and keep it going for the entire duration. This is a very compact mission, so you got to do everything you need to do in a short order. So it actually becomes a little more problematic at Shackleton, but it certainly is achievable for the mission duration within Cabellas. And again, as I mentioned earlier, slopes are reasonable, but slopes on them at Shackleton, not so much. This just shows you a little roving plan, a traverse plan, and I don't really have time to go into all the different stations that we visit here and why we would visit them. But as you can see, we cover a variety of length scales in terms of overall distance traversed and the kind of features we visit, rims of craters and the different ages of freshnesses of craters and so forth. As we go along, we also replan along the way according to whether we discover something or not. So this is just a notional traverse. Again, need to find out where the good stuff is, got to map it out, understand what the geologic setting is, need to carry out measurements that confirm the existence of these things and establish their abundances and find out their actual physical form, which speaks to their exploitability. The landing sites we're talking about, we need surface mobility in order to actually carry out the prospecting, obviously, and so that defines the kind of real estate we go to. Short duration sunlight sites may contain both subsurface and surface bound volatiles and therefore make it more attractive. But the persistently lit locations such as Shackleton Rim, not so much so. And so in my view, the trade-off here is that even though it's a riskier and shorter duration mission, the payoff is potentially very, very high. Thanks.
Thank you, Rick. Again, if there's
questions for Ross.
That's right. If there's one question, we'll take it. But otherwise, we'll go. Oh, Mike, all right.
Hey, real quick. It seems like one of the remaining high uncertainty areas, based on a question I asked Jen the other day. You know, we keep using the term this fluffiness down in that area. And the slope is only one portion of trafficability. That fluffiness may also be. If you just have any thoughts on that, I'd appreciate it, because it looks like that could be a tough one.
Short thoughts.
Yeah, got to go there and see. I think you land in a place where you have some indication that you've got fairly consolidated regolith. So landing in sunlight obviously makes a lot of sense because you have better assurance at that location that it's going to be like lower latitude regolith that you know is trafficable. And then you can branch out from there and see if you can get yourself stuck in a place that's interesting. No, that was...